think most people are here that we're expecting. So I'm just going to hand over to Simon to do the first demo.
Thank you, Valerie. And so I will talk to you about some works we did in Le Mans on generally transport of wave in disorder media and the particular framework that I will consider will be the one of disordered waveguide. So wave being reflected, transmitted in a waveguide with disordered media inside. And this work, so the two subjects I will present have been made with Felix from Le Mans and also Felix from electronics in Rennes, which is in France, not far from. So as I said, I will focus on two aspects which explain this not quite in my title. The idea is not to consider simply the transport through disordered waveguide, but to add a bit of regularity to it and to see what are the consequences of this. The first one will be related to adding symmetry in disordered waveguide, and the second one is a problem you will see related to going somehow continuously from disordered to regular through correlated disordered waveguide. So to present the first problem, we can consider this really simple experiments. So the first one is I have a homogeneous waveguide, and in this waveguide I put some opaque barrier. And in the following, by opaque I mean not completely opaque, but something which is very poorly transmitted. And so, if I send a wave on this opaque barrier, naturally it is mostly reflected and only weakly transmitted. Now what I do is that on both sides of this opaque barrier, I add some diffusive disordered media, so two slabs of randomly distributed scatterers. And naturally, what I do is that I accumulate somehow the opacity of this plus this plus this, so it's more opaque than the practical. No surprise. What changes is now, if I do the same experiment, but on the right part of the barrier, what I do is I choose a pattern of position of the scatterer, which is exactly the symmetry of this one with respect to the barrier. And then what we observe is that the transmission is significantly enhanced. And in particular, as we will see, the transmission is higher, and it can be really higher than the transmission of the barrier itself. So it's more transparent with this than it was with the barrier. So to go further, I will introduce some basic notions on the tools we use to study this. So first we have this waveguide, the barrier, and some diffusive media in between. And what we will consider is a multimodal wave propagating in the waveguide. So which is described here with this incident and reflected part, and on the other side, at the right of the heterogeneous part, the transmitted wave, which is also written as with multimodal components. Here there is no approximation. You will see after that we are mostly high frequency. So typically we have a few hundreds of propagating modes in the lead. So the lead means the two homogeneous part on the left hand. So what we do now, so with some numerical method that I described 2 weeks ago during the workshop, we can determine this model correlation and have this transmission matrix, TMN, which we restrict to the propagating mode only. So it is n by n, and in the following, n will denote the number of propagating modes, and as is, it will also denote the frequency. So the larger n, the larger the frequency. And when we have T, we can calculate with this classical Landauer formula the conductance of this system, which describe the capacity of the system to transmit a wave. So it is more or less the energy, mean energy flux, which is calculated with this formula. And to fix the idea, if I have nothing in the waveguide, so the waveguide is empty and perfectly transmitting, G is n, the number of propagating. So the maximum value of G is n.
So with this, you do not look at modal conversion to take the trace.
I take the trace of this, yes.
So you are looking, you don't want the energy to be transmitted to the other nodes.
It can be seen as some average quantity. So the idea, a way to understand this is that you send unit energy on all modes, all the n propagating modes, and you calculate the corresponding energy flux, neglecting all this interaction in this formula, but in the calculation we do to have T, we do the exact calculation of the exact solution of the wave. So we take into account all the fields. Okay, so this is one result here. So it's made on one sample only, meaning that I do not average on many realizations of the disorder. So I take one sample, and what I show here is the conductance of in three situations. So the barrier alone. So we have this black curve here. So which shape is related to the model of barrier we have chosen, and this is not a key point of this problem, because as soon as this barrier is opaque, no matter the model we choose. So here, for example, we have a very simple model, which is that we impose, so it's an infinity C barrier, and we impose that the action derivative of the field is continuous, and the field has a jump, and by setting this jump, we can have a more or less compact value. So we have this value of conductance with frequency. Now we add the diffusing medium on left and on the left part and the right part of the barrier, and we have this conductance, which, as it is measured on only one sample, we have this fluctuation of the conductance, which are classical for this case of solar media. Yes.
So is this only true if you have the same realization on both sides, or do you need just the same statistics of the realization?
Well, this is present. It's true if I have exactly the same pattern on the left and on the right part. But to add to my answer, if I do this on only one sample, I see this enhancement. Now, if I average on many realizations, I will still see this enhancement. So it can be observed on only one sample, and it resists to average. And so what we see here is that in the case of the symmetric arrangement, we have a strong increase of the conductance due to this symmetry. I go back to my the tools I will use, and so classically when we study transport in disorder media, we distinguish three regimes of transport with one parameter, which is the mean free path, which is function of the mean distance between the scatterers and the scattering cross-section of each. And so depending on the length of the slab regarding the mean free path, if the length is small compared to the mean free path, we are in ballistic, what we call ballistic regime, so the wave is only equally scattered, weakly scattered by the slab. If N is large compared to L, but small compared to what we call the localization length, which is typically N times L, L being the number of propagating nodes, then we are in the diffusive regime. And if the sample is very long, then we enter the Anderson localized regime, which is characterized by an exponential decrease of the conductance, so the material becomes really opaque up to perfectly. The conductance for the ballistic regime, since we have only weak scattering, is close to the maximum value of the conductance, so it's close to transparent. And in the diffusive regime, we are in the, I would say, classical Ohm's law, so the conductance decrease as the inverse of the length. So, in other words, the resistance increase linearly with the. Now, what we will do is, since G is defined as this, we can write G as the sum of the eigenvalues of this product, and we will see how these eigenvalues are organized in different regions. So, without surprise, all these eigenvalues are close to 1 in the case of ballistic, so weak scattering regime. In the case of the localized regime, so I do not put all the details, but you can have in mind that the first of these eigenvalues has a quite low value, but it is much larger than any other, so the transmission is dominated by only one transmission eigenchannel in the localized regime. And what we see in the diffusive regime is this characteristic form, where we see that we have an accumulation of eigenvalues close to 1 and an accumulation of eigenvalues close to 0. And if I plot this as a distribution, this is a known and well studied result, which is called this bimodal distribution of the eigenvalues, which follows this law, and where we see this accumulation close to 0 or close to 1. Close to 0, these eigenvalues are associated to what we call closed eigenchannel, so which the information they have is that of waves being mostly reflected, and close to 1 is associated to open eigenchannel, which are mostly transmitted. So this medium, which is generally opaque, can be also close to perfectly transparent if we carefully choose the incident wave. Now, if I go back to my system, I can check this bimodal property, which is really characteristic of the diffusive disorder media. And I will consider 4 different situations. One with only a slab, one with only the slab but symmetrical. Then the slab with barrier without symmetry, the slab with barrier with symmetry. So, the general case in which the theory of this bimodal distribution that we established this one, and without surprise, we check perfectly this bimodal law. If now I have a barrier, what I see is that I lose this law, and I only have low value eigenvalues with this kind of cutoff, which is related to the opacity of the barrier. So the stronger the opacity, the smaller this cutoff. And I no longer have this high eigenvalue in the case of disorder pre-barrier. Now, if I add the symmetry with the barrier problem, surprisingly, and I have no explanation for this up to now, I go back to this bimodal distribution. So this medium behaves as a classical disordered medium in the diffusive regime, and I recover this bimodal distribution. And the last comment we can make is, if we compare, so without barrier, no symmetry or symmetry, in both cases we have this bimodal law without much surprise, but we will see after that there is this effect of symmetry. So symmetry has no effect if there is no barrier. Okay, so I go back to this rapidly to this plot, just to say that, so we know that we play with the length of the slab, so the length L of this slab. I know that if L is 0, I have the system with only a barrier, so it is this movement. I know also that if the length goes to very large values, I will enter the context of the localized regime, so the computance will go to 0 exponentially. And I know that somewhere in between, I can have this enhancement. So it means that possibly I can optimize the length of the system to reach the maximum of the symmetry. So this is what we try to do here. So on this plot, what we see is as function of the length of the slab, which here is normalized by the mean free path. I show the conductance of this system, barrier plus symmetric arrangement of scatterer, for different values of the transmission of the barrier itself. So tau is the normalized conductance of the barrier. So including tau means that the barrier is more and more transparent as I go up. So for each color, I have one value of this. So we see different things on this. The first one is that indeed we reach a maximum for a given value of tau, so of the barrier transmittance. We have somewhere a maximum of the conductance when we play with the length of the symmetric slab. And I will go rapidly on this, but we compare different methods. The colored dots are the direct full direct exact solution of the wave equation with the method that I described during the workshop, which is a model formulation of this problem. The square here are obtained with random matrices. The idea is this one. So I have my disordered system, and what I say is that on a layer of width, the mean free path, I consider that a random matrix can describe the scattering of the system because the wave is completely randomized on this length by definition of the slice. So what we do is that we describe this small slice with a random matrix, but we impose to this matrix to fulfill two algebraic properties: the symmetry to account for the reciprocity of the system, and the unitarity to account for the energy conservation. Then I can do the same for each slice of width L. And using the Redeffer product, which is not written here, but it's a product allowing to combine scattering matrices, I can have the global scattering matrix of the system. And then from this, I can, in the scattering matrix, I have the transmission matrix, and from the transmission matrix, I have the product. Yeah. For one slice, I generate randomly a matrix. So it is really random of n by n, 2n by 2n. And then with some, so I do not have the details in mind, but it's really a very short process to have it. I impose, so I construct a matrix from this randomly generated matrix. I compose this scattering matrix which has to respect this property. So it's completely random.
Yes, you are not sure that this matrix comes from fraction problem.
No, it's really random at the beginning, so there is no information of where it comes from, the wave equation is from. I only impose that it describes a system that is strongly scattering, so hence the fact that I choose a random one, and that it has to describe a reciprocal and conservative system. And it is the only information that has this.
So scattering amplitude of individual scatterers is not there.
No. No.
But also the statistics of the scattering matrix, and how do you know what statistics?
For this matrix?
Yes. You just put a Gaussian statistics on.
For the initial one, I don't want to say something I don't remember, but yes, we have to fix a choice of the distribution of the initial one. Let's have a try to do that.
That's why we say in different terms. So the model is different from one to another.
Alors, different curves, you mean?
Yes, so here we get different colors. Sorry, I haven't.
So each color is for one color is one value of tau, the transmittance of the value. But for one choice of tau, for example, the green curve, so the full dots, circle dots are the numerical solution of Helmholtz. The square dots are random matrix solution of the random matrix theory. And the continuous line, I will show it now. Speak. Yes.
Can you tell us how you multiply the matrices? Is it matrix or multiplication?
I don't know, it's not matrix multiplication. We could do this with transfer matrix. But here it's a bit more complex product. But it is obtained by writing mode matching at both ends of the slice. And then you have rules to obtain a scattering matrix from scattering matrices. So it's not detailed here, but you have these rules which are easy to find by writing mode matching.
It's mimicking somehow this symmetrics you had before, layer by layer.
It exactly calculates the product itself exactly calculates the scattering matrix of the ensemble. The only approximation made here is that we describe this with random matrices instead of really solving.
You cannot prepare that by only one random matrices.
No, when you do this, you miss one important aspect of the disorder is that the scattering is somehow cumulating. So, for example, if I consider only one random matrices, only one slice, statistically I will have probability of going back and going forward, which is equal, because it's fully randomized. So if I want to describe a chaotic system, typically one random matrix will be okay. It will describe this. The difference between this chaotic system and the disordered system is that here, if I consider a larger size of disordered media, I will lose this property of having an equal probability of going located or transmitted. The transmission will be lower and lower. And to account for this, I have to consider scattering process only at the scale of the mean free path, and then adding this layer by layer. And so yes, the third model is some empirical, a very simple empirical model, and it will describe these continuous lines. The idea is that we write the resistance of the system, so which is the inverse of the conductance here, as being simply some series model. So I write that it is the resistance of the diffusive slab, so the slab alone, plus some fictitious, somehow resistance of the system, which will be the barrier plus the effect of symmetry. So I do not need the detail, but what we do is that we guess some form of this function, so which is we guess a simple form of this function, and then we impose the limit condition. This limit condition means that if I have if L is 0, I have to find back N tau, which is the conductance of the barrier alone, and if tau is 1, I have to find back, so it means that the barrier is perfectly transparent, I have to find back the usual OCO conductance of a diffusive slab alone. So imposing these two limit conditions, and after some calculation, I find that GE has this form with some parameter tau c that is found numerically by fitting this, but it's the only free parameter, by fitting this form. And then I can test it, and I see that it describes well all this situation. The advantage of this really simple scaling model is that now I can find where is this optimal situation. And for this, what I do is that from this equation, I search for the value of S which maximizes G, so which minimizes this resistance, and I find that it is this solution, given the transmittance of the barrier and the factor tau c. And if I apply this to the formula, and I assume also that tau is an opaque barrier, so tau is small, what I find, surprisingly, is that G optimal, so the optimal conductance, is half the value of the diffusive conductance of the slab. Meaning that when it's optimally settled, this system behaves as a simple classical diffusive system, but which is half the length of the initial one. Okay. So now we will add losses, and this is where you see the difference between physicists and mathematicians. And if you want to know the difference, you give them two problems, one is lossless. The physicist begins with the lossless problem because it's easier. And the mathematician begins with the lossy problem because the lossless problem is easier. So as you see, I'm a physicist. I prefer lossless problem. So without losses, we have seen that we have this ballistic diffusive localization, this characteristic decrease of conductance. Now, if we have losses, we will distinguish between two diffusive regimes depending on this SA, which is typically a length of absorption. So how rapidly is the wave absorbed due to the losses mechanism. And if L is smaller than this length of L is the length of the slab, and this length of absorption, we are still in the classical diffusive regime, so what we call the weakly absorbing diffusive regime. G decrease as the inverse of the length, so the Ohm's law. And if we go to more strongly absorbing system, then what we see is that G is mostly dominated by an exponential decrease of the conductance, and for the anecdote, it is one of the reasons why it's so difficult to experimentally implement the Anderson localization. It's because Anderson localization is a regime of exponential decrease of the conductance. But when we measure it experimentally, it may happen that what we are measuring is not Anderson localization, but strongly absorbing diffusive transport. And distinguishing between those is not always good. So quickly, what I show here is the equivalent of this. So this was lossless, this is with loss. What we see is that we can still reach some maximum. So we have still this effect of enhancement due to symmetry. But it is naturally, without surprise, it is weaker when compared to the lossless case. And also, rapidly, when I increase the length of the slab of the system, I enter this regime where it is dominated by the losses, so everyone is decreasing exponentially here due to this loss mechanism. So this effect of symmetry-induced enhancement of the conductance is robust to losses, but it is clearly weakened by this losses. And so, just an illustration of it. What I have here is the example of the barrier, a symmetric slab, and no absorption. So we see that we have a significant transmission of the wave. The same with absorption. So it is clearly less efficient in terms of transmitting the energy, but I still see some field being transmitted through the barrier. And now, if I have no symmetry and absorption, so I could play with the color map, but clearly it goes very rapidly to zero. And what I see here is that the wave is concentrated in the left part, and there is almost no transmission. Yes, we can play with the scaling model I showed, and from the scaling model, we can see that the enhancement of the conductance, so which is the ratio of the conductance divided by N2, which is the conductance of the barrier alone. So this gives me the enhancement, and the enhancement scales as the inverse of the square root of tau, the conductance of the barrier. So which means that the more opaque the barrier, the more strong this effect of enhancement. And this what for any frequency, because we tested different frequency, I call the N is the number of probability mode to give me information on the frequency. And by the way, we also see, so this is results of full numerical calculations, and we see the meaning of this tau c we had in the scaling model, the simple empirical model, is that we observe that for transmittance of the barrier larger than tau c, we have no enhancement, no effect of symmetry, and this effect of symmetry begins only for tau smaller than this tau c. And this is afterward we see the meaning of this numerically estimated value. This was lossless. With loss, what we see is almost the same, except that for very opaque barrier, rapidly this effect is dominated by the losses, and we have this kind of saturation of the enhancement, and the enhancement then is driven by the losses, driven by this apportionment. And we have this, again, empirical law that gives us the maximum enhancement we can obtain for a given level of losses. Okay, so we have seen the losses. Now what we can consider is how robust it is to symmetry breaking. So we have this effect of strong enhancement when we have symmetry. So the conductance of the barrier alone is 9 here. If I put something symmetric, I have the conductance which is much higher than silver. And now what I will do is I will progressively move some of the scatterers. These are the red one. I move 1, then 2, then 3, etc. And I measure the conductance, so the mean, the average conductance of many realization when I break this symmetry. And what I see is that it's very sensitive to symmetry breaking because for a low ratio of shifting scatterer, it drops very rapidly. And as we have seen, after some importance of this symmetry breaking, I go below the level of the barrier itself, in the case we have seen in the beginning, which is a non-symmetrical slab, which is more opaque than the barrier. So we can go a bit further, and to do this, we will play with random matrices. So we will model this system with slices with random matrices, and what we will do is that we will change some of the slices by other matrices to break the symmetry. So for example, here I have changed 2 of the slices, so I put another random matrix instead of the symmetrical one with the split. And what I will consider now is the effect on the conductance of the number of slices I have changed and the distance from the barrier to the closest modified slice. The result is this one. So what we see here is, so the different colored dots gives me the number of slices I have modified. So in some way the amount of symmetry breaking regarding this symmetric situation. And in abscissa, it is the distance from the nearest defect to the barrier. And what we see is that the prominent effect is this one. So when I change the number of slices, the number of slices which are non-symmetrical, the effect is less pronounced, and what is dominating is this one, meaning that if I change slices far from the barrier, I can change many slices, it has no big effect. If I change close to the barrier, I can change only one, it has a very strong effect, and typically, here, if I change the first one, I completely destroy this symmetry induced on announcement, so I go to the level of the barrier alone. If I do changes far from the barrier, I stay quite to the optimal value. So the driving parameter is this one, so it means that it's really sensitive to what happens at the vicinity of the barrier. So an illustration here, the same wavefield as I showed already. Now what I do is that I move some scatterer, so it's no longer scattering matrices, random matrices, it's the exact solution here of the wave equation. I move some scatterer here. I see that I still have a reasonable level of transmission. Now I move the same amount of scatterer close to the barrier, and I see that I go to a very low level immediately. So I use this symmetry. Another way to break the symmetry is to move the barrier. So I keep the symmetric distribution of scatterer, but I move the barrier. So to do this, what we have done is creating a small gap, so which is the order of which is typically the wavelength. So it has no real effect on the symmetry announcement. So we can see here at this. The barrier alone, the barrier with non-symmetric disorder, the barrier with symmetric disorder. So it looks a lot like the first result I showed. And now I will move the barrier by a very small amount, which is lambda over 2000, lambda being the wavelength. So it's really, really much smaller than this gap. And I divide the level of conductance by something like 2, something like this. So it's really, really sensitive and sub-wavelength sensitive to this symmetry. Here is an illustration where I shifted the barrier by lambda over 10, so 1/10 of the wavelength. And you see this difference in the level. And another way to see this is this one. So what we show here is the average conductance as function of the shift in the position of the barrier. The right or to the left.
When you moved the barrier, did you fill the gap that you created with particles at the same density, or have you just created a layer which has no particles in it?
Yeah, when we have made the arrangement of scatterer, we have created a small gap to have the room to move the barrier. So this gap is very small, it's one wavelength. The wavelength being typically here we are 300, so it means that in the width of the waveguide we have 150 wavelengths. So it's really, here it's exaggerated, it's really a small gap. And inside this small gap, we do an even smaller motion of the barrier. And so what we see here is this very strong sensitivity. So the optimal situation, perfect sensitivity is here. When we move, so when I move one lambda over 200 as I showed, I divide by something like 2. So it is a zoom on this central part. And when I move by 1 over 50, typically, so it's here, 1 over 50, then I drop to the level of a non-symmetric situation. And we see that with non-symmetric situation, we can move the barrier as we want, we do not change the level of conductance. Something which was unexpected and still unexplained is that after this 1 over 50, we go below the level of the non-symmetrical conductance until some value which looks a lot like a quarter wavelength, and it is very robust from one situation to the other. We always see this rise of the conductance at the quarter wavelength, and then it goes back to the level to a very large value of wavelengths. There is no difference between non-symmetric and symmetric because we have completely broken the symmetry of the system. So this is still not explained, and we try to go further on this, but for the moment there is no answer to this effect, but quarter wavelength suggests that there are some strong coherent effects between this. Okay, I finish this first part with an experiment that has been made with colleagues in Israel. So it's in a metallic, so it's a metallic cavity rather than a metallic waveguide with metallic scatterers, and we are in the microwave regime. So it's electromagnetic waves. And so typically, measurement has been made in this regime, so between 11 and 17 gigahertz, and the size is 50 centimeter and 25 degrees. So I just show these two results. This one, which is similar to the one I showed with numerical results, so as function of the frequency, where we compare the barrier with zero scatterer, so the barrier alone, the bigger, the barrier with scatterer without symmetry. So in this experimental case, we do not see a strong difference between both. And when we put some symmetric arrangement of scatterers, and we get this increase of the conductance. And this curve has to be compared with the one I showed with many colors. So here we play with the number of scatterers, which is equivalent to playing with the length of the slab. So the larger the number, the larger the length. And we compare the non-symmetric situation where the conductance decreases with the size of the slab. The symmetric situation when we have this local maximum, so this optimal enhancement of the conductance, and we compare with the diffusive model, which is the empirical model I showed before, but accounting for losses. And we see that it fits quite reasonably with the measurement, except here that globally we have the same trend. So with this experiment, we have evidence this system experimental. Okay, I switch to the second subject. So we will no longer speak about the symmetry, but we will keep in this with this bimodal property that I showed before, and I said that it's really characteristic of disorder medium in the diffusive regime. So we know that in this diffusive regime we have this repartition of eigenvalues which are either associated to fully reflected wave or fully transmitted wave, or at least strongly reflected and strongly. What we know is that in a perfectly regular medium, so periodic medium for example, we are in the Bragg scattering regime, meaning that, to say it simply, the medium is fully opaque or fully transparent, depending on either we are in a transmitting band or in a gap between two bands. And the question is, what is the fate of this property, characteristic of this medium, when I go from disorder to regular? So if I add some regularity, do I lose this property? So I know that at the end I will lose this property. But how do I lose this property? What will be at some threshold or and so a good candidate to see how to go from one to the other is to use the hyperuniform material. So it could be the second time here. Hyperuniform material at install. So since we have already discussed this, I will not spend a long time on presenting what it is. What we can say simply is that, so we will first consider a fully disordered medium, so we have a pattern of points. And now if I take some volume in this distribution, so here a disk in And what I will evaluating is the number of points in this volume when I increase this volume, and in particular the fluctuations, so the variance here of this, how it evolves with increasing. And for Poisson distribution, we know that the variance increases as the volume itself. So here R to the power 2. In the case of periodic pattern, we know that the variance will increase for large R, will increase not as the volume of the disk here, but as the surface. So it's R to the power d minus 1, so R into. And what we will call hyperuniform pattern is all the patterns, regular or disordered, for which the long-range density fluctuation, so meaning the variance divided by the number of average number of points, so relative to the volume, goes to 0. So it this long-range fluctuation vanish at long scale, and this is what we call hyperuniform. So periodic media are a particular case of hyperuniform because it will vanish at long scale. And precisely, the idea is that at large scale, this looks like some regular model. In Fourier space, the equivalent of this property is that at long wavelengths, so for Q going to 0, the structure factor will go to 0. And any pattern which has this property of Q going to 0 is an hyperuniform distribution of points. Among this hyperuniform system, we will focus on a particular one, which is called stealthy hyperuniform. And it's the system for which S is 0 on a finite domain. So, for example, here on a disk around 0. So, for all Q which modulus is smaller than the value, given value, S is 0, and this is what is called this stealthy hyperuniform. This hyperuniform is SHU, can be described, the degree of correlation can be described by the stealthiness parameter, which is given here, and what is useful for us is that it can be used as some continuous setting of for the medium between t equal to 0, which will be a uncorrelated disorder, and the perfect disorder, which will be at a starting point, and t reaching some maximum value. And so for this criteria, the maximum value is close to pi over 4, and at this maximum value, the medium is perfectly regular and correct. So to illustrate this, I show here three examples or three values of this stealthiness parameter, and the experiment we will, so the numerical experiment we will do is this one. So we generate some hyperuniform distribution of points, and from this we define this regular grid on which we have a distribution of points which reflects this hyperuniform distribution. Of course, solid schematics. In practice, we have 2000 scattered in the slab. And what we show here is typical repartition of the points. So we see that the regularity increases, and we see here the structure factor. And on the structure factor, what we see is that for low value of the stealthiness, we have this transparency zone, which is where the structure factor is put to 0, up to some value, the 2c that I have fixed, and which is related to this key value. And for larger frequencies, for larger volume numbers here, I go back to the classical diffusive medium described by this quite anisotropic here distribution of values for the structure factor. And the medium will behave as diffusive and isotropic. When I increase the value of the stealthiness, what appears here is that close to a value which corresponds to the Bragg frequency, which is a red circle here, I have a local increase of the structure factor to kind of anisotropic here bump of this value, and which is somehow a precursor of the Bragg scattering, which begin to appear in this system. And we also see the second circle, which corresponds to 2 times the Bragg frequency. And if we increase, then we enter the crystalline regime, so we no longer have this isotropy of the system, it becomes strongly anisotropic. And what we see here is something approaching the theoretical structure factor of the periodic medium, which will be only spots corresponding to all the Bragg eigenvectors. And here, so we are closer and closer to the situation of Bragg scattering and so what we will see now is we will put this system in a waveguide and send the wave in 3 situations. One is at a frequency which is below the Bragg frequency, one is at a frequency which is close to the Bragg frequency, which is this circle here, and one at a frequency above the Bragg frequency. And we will consider the conductance of the system and the distribution of the eigenvalues to check this model property. So first, we start at a frequency which is lower than the Bragg frequency. So we are here, and what we see is that when we increase the value of T, first this frequency is in the diffusive part, the non-transparent part. So we expect a low value of the conductance, and then this circle, this black circle will increase, and after, what we see here, this pink circle is inside the transparent zone, so we expect something perfectly transparent. And this is what we see here. We have, for low value of the stealthiness, a low value of the average conductance, and we can check that it corresponds to the diffusive, expected diffusive value of the conductance. For larger values of the stealthiness, we have a larger value, so it's not exactly 1, and why it's not exactly 1, although we expect 1, it's because of this pixelization of our system, which has the consequence that the hyper-uniform medium which was generated is a bit moved, so slightly, so it does not compromise the results, but the consequence is that it's not perfectly zero in the black zone. So we do not have a perfect transmission here, but close to perfect. But what is important here is that the transition is very abrupt. So abruptly, at some threshold value, which is close to 0.3, we go from diffusive to transparent. And what is interesting also is that we could compare this to a simple calculation which consists in somehow integrating the structure factor, meaning that I integrate all the possible directions. So I take the structure factor and I rotate all the possible directions for a given value of the modulus Q, and this gives me some integrated structure factor. And I know that if this structure factor is large, the conductance is expected to be low, the structure factor is low, the conductance is expected to be large. And if I compare 1 over f to g, I see that the scale, at least the scale of this abrupt transition is well described by this factor, meaning that the scale of this condition is mostly driven by geometrical aspects rather than by the wave physics of the problem. So it's mostly of geometrical origin related to the pattern of the spectrum. Now we can consider the bimodal distribution. So at this value of the stealthiness when we are in the diffusive regime, we have the bimodal distribution. We will check. After we enter the transparent regime, and we see that we use the bimodal, and in particular we use the no value, meaning that the conductance is much larger because we have only high value, sorry, of the transmission of the. Here it's the same, but it's just another way of representing this property. We can expect this distribution of this value of the eigenvalue, that function of the values. And here is some summary of this. It's the value of the transmission eigenvalue, that function of the stealthiness and the index. We see here the bimodal, large value, small value, and then abruptly large value everywhere. So the transparent regime at a very abrupt threshold. Now, if I do the same at the Bragg frequency, or close to the Bragg frequency, so first maybe I can go back to this. So it's the red circle. So first I am in the diffusive regime. Then I see this local increase of the structure factor, so I expect a significant effect of scattering. And then I am in the transparent zone. So here, what we see is that effectively we have this part where we are in the diffusive regime. Then we enter a zone where we go from this isotropic diffusing system to something approaching the Bragg scattering, so also the anisotropic behavior. And because of this, again, if I go back to this, what we see is that depending on the direction of the wave, or for us, depending on the realization of the disorder, we can have strong scattering or small scattering. And for this reason, one of the consequences is that first, in average, the conductance decreases, and after we are well entered in the transparent regime, it increases. And if we compare again to the inverse of this integrated structure factor, we see that again the geometrical property explains most of this average behavior of the conductors. Something which is surprising, at least not expected, is that the bimodal behavior is quite robust to this. And in all of these cases, we follow more or less the bimodal property, so it appears that bimodal is not strictly a characteristic of diffusive disorder, but it is a more general property, even when we have strong correlations. The last one is above the Bragg frequency. Again, if I go back, what I see is that I am in the diffusive regime, I am still in the diffusive regime, and then, since I am above this Bragg frequency, it will be also strongly dependent on the orientation of my wave or the realization of the disorder. And so I have first this diffusive behavior, and after I enter the crystalline zone, which is shaded in gray here, I have a behavior that here is an increase of the conductance, but depending on the choice of the frequency, we could expect other kind of behavior, and typically, in this case, yes, if I compare to the structure factor, the inverse structure factor, I see that it's not fitting well. Probably because this very simple explanation is no longer relevant, it's more complex situation. Okay, I stop. And what we see is that we keep this, again, this bimodal distributions, which looks like it is very, very robust to this correlated disorder. I skip this, and switch.
You don't need to do that. Go back into the next slide.
Thank you. It will be quick. It's just to illustrate with another experiment, this time in acoustics. So it looks a lot like the first experiment which was in microwave. We have a waveguide, so it's seen from above, with a circular sound arc scatterer in different configuration of the disorder, or electric disorder, so 4 hyperuniform distribution. We see the same kind of result here, also simulations. And what we wanted to do here was to compare simulations and experiments. Qualitatively, it works quite well, except this small shift between the gray, simulator, and blue experimental. And it's mostly probably due to the fact that the model of losses is innate, is not accurate enough to account for the losses and the proximity of the scatter. So the gain losses are probably. But what we see anyway is that we are able experimentally and numerically to catch this effect of increasing order, and in particular the appearance of the bright scattering with this, for example, with this gap here, which progressively appears when we increase the order. Okay, just a minute.
Thank you so much.
Model than hardware. And also I wanted to ask you, what is the physical interpretation of the enhancement of the transmission due to the signal?
Alors, pour so for the barriers, so maybe one simple way to figure this out would be first considering a small barrier which is made of a very dense material. And if we go to the limit of an infinitely small barrier, it can be described simply by jump condition of the field or the derivative of the field. So for example, what we made for the simulation we showed was to say that the derivative of the field has no jump, and the field itself has a jump which is settled with the value of the derivative. And alpha is some parameter I can adjust to have a stronger or less stronger profile barrier. But as I said, it's not really important, because if I choose another model could be non-continuous, and if the issue is jumping, I will observe exactly the same way. What is important is that I have a strong discontinuity due to the barrier, hence a strong opacity. But it's not really important, the microscopy, I would say.
I'm just trying to understand why is the signal helping you so much?
I also try to understand.
No, I think you have a layer. By doing symmetry, you have a layer. A layer, you have a resonance. That's what example to see.
What is sure is that it's not a resonance effect, because it's very broad band, and so it's not related to any resonance. One guess we have is that it looks like this more well-known effect of coherent setting, where you send a wave on the diffusing medium and measure the reflected wave. And what we know is that in the direction of the incident wave, we have a local maxima, which is twice. And this can be explained by reasoning on some coherent trajectories of the wave in the medium, which makes loops that can be can be followed in one sense or another. So with the end, as I explained it, but we have hope that using this kind of tools, so we don't need a trajectory to relevant paths, things like this, we could explain this effect more microscopically, and also the fact that, as I showed, it's very sensitive to the cause the activity of the area, and it is also a clue that it's related to this kind of coherent path close to the boundary. And another idea is that if I have symmetry and no barrier, I have no effect of the symmetry, although I could also include this kind of thing. So this is somehow complex. We try to explain this, but at the moment we are with this numerical observations and no satisfying distribution.
That's part of that random influence of bodies is very strong. So can you imagine that this would work? You can have a week fluctuating movement and things like that, like that.
Yeah, it's also something we have in mind and an open question for us. For the moment, we did only fully disorder, but still diffusing, not localized. So we tried in a localized review. It's still, we still have this understanding. Let's comment the what we do. But what we could try is to see whether it can be observed in other kind of media, like the US CNRS or structure in other ways.
But having a weak fluctuation, because your vision is very strong, and you have very strong fluctuations, right?
Situations
Or
are
it's like the random vision, whatever the strong vision,
we are in the what we use to name the deep value, so it's far from ballistic. So we are really strongly scattered.
But I mean, you can achieve that with weak fluctuations in the random vision, which is not big enough. So that's not like not any originalities, are they like strong patterns?
Again, it's not really important, because we can use very simple models where we only locally and slightly capture the otherwise homogeneous media, and really the symmetry of the pattern is so strongly or not strongly taken.
Okay, barrier, symmetry. Barrier again.
What I know is that symmetric, two half slabs being symmetric, I have no effect on this. What I really need is typically if I do transmission between the disorder medium and the same being symmetric, but without zero. That I have no effect. I measure this for any diffusive medium having the same length, they have the same length. So what I really need is symmetry plus this strong effect of capacity barrier. In this case, I can imagine that I will not see the effect of symmetry because what I will have is something like this, but with barrier on both sides. It will not make a difference between something not symmetric and symmetric.
In this case, the barrier will
Possibly. One guess we also have is that if we consider the quasi-normal mode that is open system, if it's symmetric, we know that the quasi-normal modes are either symmetric or antisymmetric. we know that if we have a strong jump like this, we will break some of this mode will not see this, because the symmetry of the mode will remain not see this, and the other half of the spectrum will see this and will be strongly active. So this is a possible idea. The problem is relating QNMs to scattering is not an easy task. It's far from it. So we are stuck with this. So we have some many ideas that still work to do.
Why you're discriminating both because it's like to find the relation jump to like this.
So I impose two different indicators and I just
Yes,
play with
try to play the
yeah, well, but we didn't try that. Yes. Mm-hmm. So you mean the associated with the eigenvector are the transmission eigenvector. So the eigenvector are the transmission eigenvector. Yes, we have tried on this side because we know that evaluating the spectrum with these tools rather than the Canadian and the India because it's simply transmission. But what we see is that for the Simon number well, the transmission eigenchannel related to high values of the transmission are close to symmetric or unsymmetric. And as far as eigenvalues get to lower values, we lose symmetry. So for the transmission eigenchannel, there is no reason why there would be symmetry. We do not have this constraint on this. But we see, anywhere, we see some symmetric property, but not really strong. Some really strong on which babies and things.
Okay, I think we're ready to close. Let's thank Simon.
Thank you.